we will be covering basically the issue which is central to the theme of the conference, which is statistics for transformation of agriculture to achieve sustainable development goals. As you know, climate change is a scientific reality. There is increasing recognition that we need the business as usual scenario of development will take us down the unsustainable path. So there is a lot of international cooperation which is happening to undo or to mitigate the greenhouse gas emissions as well as adapt to the impact of climate change across the world. So we have two distinguished panelists. Almost all the panelists are from outside India. So we will have a very rich perspective of the issue at hand. Without much further ado, I would request Elisabetta from Italy to speak to us on monitoring the agri-environment. You will have roughly 20 to 25 minutes, depending on if the two people come, though, then we'll have to scale it down. So you please go ahead and you can make the presentation. We will take questions at the last. We'll reserve about 10 minutes or so for question and answer sessions. Please note down the questions and be brief so that we can spend more useful time clarifying or answering the question which is central to any conference discussion. Thank you.
Thank you, Mr. Chair. Good morning to everybody. I'm going to talk about agro-environmental indicators. First of all, let's try to define agro-environmental indicators. It's not so easy to have clear ideas about the meaning of this word. What is that? Indeed, several institutions have been working on the definition of agro-environmental indicators, and we can refer, for example, to the definition that has been given by FAO, that is the following: agro-environmental indicators are key tools to monitor the environmental performance of agriculture and track trends in the environmental impact, as well as to provide policymakers and citizens with useful information to assess the effects of the integration of environmental concerns into policy measures. This is a very important definition. The point is, how can we measure that? Indeed, the agro-environmental indicators have been subdivided into 5 main domains based on the model which has been developed by the European Environmental Agency, and which are the following: driving force, pressure, state, impact, and response. There has been a lot of cooperation between Eurostat, OECD, and FAO for developing the main agro-environmental indicators. And OECD listed about 18 agro-environmental indicators. And these indicators are strictly related to at least 3 of the Sustainable Development Goals. Number 2, end hunger, achieve food security and improve nutrition and promote sustainable agriculture. Number 12, ensure sustainable consumption and production patterns. Number 13, take urgent action to combat climate change and its impact. But still, we have the problem of identifying the way we can measure these indicators. Also because they are generally complex indicators and require a variety of measurements. Let's try to understand a bit better how we can do that. So, some agro-environmental parameters are related to agricultural management practices and may request farmers' interviews. For example, the use of fertilizers. In order to understand exactly which is the level of input used by the farmers, we have to interview them. But also concerning cropping rotation practices, we have to make some interviews. But also even for some specific land uses, if we have fallow or abandoned arable land. In some cases, we even need some administrative information, like the case in which we need to know which are the farms under a specific policy measure, that is Natura 2000. Some other indicators require some laboratory measurements. For example, concerning the quality of the soil, we need to collect the soil on the ground, and specific measurements have to be made in the laboratory. Some others can be collected directly on the ground through ground observation, or even through an analysis of aerial photos or high-resolution satellite images. Several of these indicators have as input some information which can be collected directly on high-resolution satellite images. For example, some information concerning irrigation can be directly derived from satellite images. The agricultural land use and land use change, and I'll talk more about this topic afterwards. Cropping patterns, farm management, soil cover, tillage practices. This information can be derived from satellite images. Trends like agricultural intensification and specialization. These are very important aspects of the impact of the agriculture on the environment. Concerning pressure and risk, resource depletion means soil erosion. Some information can be derived about soil erosion from satellite images. And also, for the state and impact, we can derive some information concerning landscape state and diversity. When we have to collect information on the ground, what we have to do is adopting a sampling frame. In the specific case, we need to adopt an area sampling frame. That means we have to select some areas on the ground on which we have to make observation. There are many different kinds of area sampling frames which can be adopted, and according to the level of spatial autocorrelation at increasing distances that we can identify concerning the specific variable of interest, we can identify which is the optimum strategy for collecting information on the ground. So what is the kind of area sampling frame that we should adopt, and which are the main characteristics of this area sampling frame? Given the spatial autocorrelation function that we can estimate, and given a cost function, we can obtain the optimum area sampling frame that is the one that is able to minimize the variance of the estimator we are interested in. But I would like to focus on a specific aspect. Quite often, when we talk about the impact of agriculture on the environment, we think of the change. What is changing? What is happening? And if we focus on the change instead of focusing on a specific value in a time, then we can notice that the spatial autocorrelation that is shown on the bottom, the spatial autocorrelation decreases dramatically when we don't focus on a specific variable but on its change over time. The spatial autocorrelation decreases dramatically. What's the impact of that on the kind of area sampling frame that we select? The impact is that the optimum choice becomes having very large area units, because if we do not have a high autocorrelation, spatial autocorrelation at increasing distances, this means that we are not collecting redundant information while observing on the ground areas around a specific point. So we should have larger units, area units, to be observed on the ground. And this is something that we should keep in mind. But indeed, since in these days we have been talking so much about satellite data classification, about the use of machine learning for satellite data classification, I would like to highlight some aspects. And also I would like to clarify which are the possibilities of application of these instruments and which are its limits. I'm going to show you an example. In this case, we have classified Sentinel-1 and Sentinel-2 satellite data. Maybe you heard about this satellite data. We can use directly for free this satellite data. These satellites have been launched by the European Space Agency, and the pixel size is 10 meters. And I think this is a huge improvement in the kind of data we can use nowadays all over the world. Well, what we used is not only remote sensing data, of course, but also ground data which were collected in an area in Italy, in Tuscany. We had 574 points on which the specific land use was observed by the Italian Ministry of Agriculture. And we selected a subsample, 80% of the units, for training the classifier, and we used the 20% of this sample for testing the result of the classification. Which classifier did we use? We used a parametric model, the regularized multinomial regression, and two non-parametric models, focusing on these machine learning tools which have been mentioned so many times in these days. And I would like to focus on the comparison of the results of the use of these different kinds of classifier. Well, what we can say is that in the end, random forest is the best, but there is not such a big difference in the accuracy among the three different classifiers. Not a big difference. And by the way, what is really interesting is the fact that the parametric model is in between the two non-parametric ones from the point of view of the accuracy. This is very interesting to me because indeed now in these days we had the impression that with machine learning techniques we can solve whatever kind of problem. We don't need ground data anymore, and this is not really the case. And in some cases we can even have that parametric model that has been used so far is even better than some machine learning methods. What is interesting to me is the fact that if we look at the result concerning the accuracy, after having made different selections of the subset for training and testing, we can see that the stability of random forest is higher than the stability of the other two models. And this is a very interesting quality, because it means that since we shall have operationally just one set of data on the basis of which we are going to make the classification, then probably we shall have more stable results using random forest. But in this case, we were using just pixels, since the data were collected on points, so we had a pixel by pixel classification. The question now is, can we have better results if instead of focusing on just pixels, we focus on parcels? It's not so obvious. Let me go back just for a minute to the previous slide, and let's look at the different classes that we have taken into consideration. There are grape trees, olive trees, sunflower, other crops. There are not so many. They are interesting from the point of view of the impact of agriculture on the agro-environment. They are not enough if our aim is producing agricultural statistics. Not enough at all. And as you can imagine, there is a very strong relationship between the number of classes we take into consideration and the accuracy that we can have. So if we want to split these classes into many more classes in order to produce agricultural statistics, the accuracy will decrease for sure. And let's look at what happens in case we take into consideration parcels rather than pixels. Indeed, I have to say that in this case, we are not really using ground truth. In this case, we are using parcels on which the farmers have made the declaration for the subsidies. So it's not really ground truth. It's information concerning parcels. And what happens on these parcels? Well, in this case, we have used many more classes than before, many more. Still not enough for agricultural statistics, enough for monitoring. In fact, we have the permanent crops altogether. We have winter arable land, no distinction among the different specific crops. So what we expect is a very high accuracy, much higher than what we will have in case we have to use this kind of information for agricultural statistics. And I had to say that really, this is not the case. So the accuracy we have in this case is not so high. Why? Maybe we are not good enough in the classification. Maybe there are some errors in the data that we use for training the classifiers. And this is very likely. Why? Because as I said before, in this case we are just using the farmers' declarations. And they are related to a cadastral information that is not really updated. But this is the common case in many, many countries. In many, many countries, the update of the cadastral maps is not so fast and it's not too frequent. Thus, if we are going to use this kind of information as training and test for classifying Sentinel-1 and Sentinel-2 data, we are not going to have a very high accuracy. And I think this is very important to keep in mind. So we can see which is the impact of high quality information on the ground on the final classification. There are some other aspects that I would like to highlight. We are used to maximum likelihood classifiers. This is the usual approach for classifying satellite images. And we know very well that if we do not use any kind of prior information, the percentage of the different crops on the ground based on ground data collection, what we are going to do is overestimating the small classes. But if we use the information we have from a ground survey, for example, that is, as I said, the proportion of the different crops on the ground survey, and we use this as a prior for fitting the maximum likelihood classifier, the result is that we are going to considerably overestimate large classes and considerably underestimate the small ones. This is something we already know concerning the maximum likelihood classifier. And the question now is, and what about machine learning? Can we use additional kinds of information for feeding machine learning? Can we embed additional information in machine learning? Can we use expert knowledge? And can we embed expert knowledge in machine learning? These are some of the topics we are working on because I really believe it's important to not rely only on automatic methods, but also try to take advantage as much as possible from information that is available and knowledge that is available. I'll have also to remind another important element that is the following. Once we have made the classification and we want to produce a kind of statistics, we have to keep in mind that pixel counting is a biased estimator. I'm sorry to repeat it, but I think it's crucial. And the bias is due to the fact that we shall have for sure some errors in the classification. And besides that, we have mixed pixels, which for sure will not be properly classified. So we don't have to rely only on the classification in order to produce unbiased statistics. We have to combine the results of the classification with the ground data through many different methods. The most well-known one is the regression estimator, but we can also use several small area estimators. Just another element. As I said before, when we talk about the impact of agriculture on the environment, we are particularly interested in the change, and particularly in land use change. How can we really measure the change using satellite images? And why should we use satellite images? Because we can have a general overview. We are not going to measure the change only on some plots on the ground, but we are going to measure the change all over a territory. But which are the two possible approaches? The first one is comparing the classification which has been made at two different points in time. Can we really do that? Well, indeed, according to De Fourny, this is not possible. Why? Because we have, as we saw before, a certain level of accuracy in the classification. That means also a certain level of error. And if the level of change in general is smaller than the level of error in the classification, we cannot really measure the change on the basis of the comparison of the classification at two moments of time. A different approach is trying to identify directly the change on two specific satellite images. And some people are working on that, but it's not so easy to do. Particularly, it's not so easy to do that automatically, of course. Just the last point, if I may. When we talk about agri-environmental parameters, we talk about complex parameters which have variables as input, many different variables as input. But these variables are observed on completely different kinds of support. For example, we can have a digital elevation model. We can have hydrology that is relevant. We can have soil information that is very relevant, that is generally observed on the point and is expanded to an area. Geology, we have specific points on which we can observe the yield and so on. So for some of these variables, we have observations on points. For some others, we have observations on small areas. For some, like meteorological data, we have observation on points, and we have to specialize this information, maybe through kriging or other kinds of techniques, more sophisticated ones. The same we do concerning the quality of the soil. We collect information on the point, and we have to expand to the remaining part of the area through some statistical models, which embed also some other kind of information, like in this case, the pedological map. So when we want to create an agro-environmental parameter, we have to combine these different kinds of information. We have to integrate these different kinds of variables. For example, let's talk about an yield forecasting model that can be extremely important when we want, for example, measure the impact of drought on an area. So we want to forecast the yield that we are going to have given the fact that we have drought. When we focus on yield forecasting model, we realize that it's generally a statistical model which has as input a set of deterministic models. For example, the evapotranspiration model, we can think of the Penman evapotranspiration model. Well, it's a deterministic model that has been created on a point, on a specific parcel. And it's one of the different deterministic models which are embedded in a statistical model. And each one of these deterministic models takes as input some of the variables we mentioned before. Let's talk about evapotranspiration. What we need is the kind of soil, we need information concerning weather and so on, precipitation and so on. So we have information that is observed on areas, observation on points that has been interpolated and so on. What we generally do then is trying to reduce all these elements to the same unit in a GIS. So if we combine all these information sources and reduce them to the same unit, which can be a polygon, but very frequently is a square in a raster GIS. What we do is combining these different kinds of information, disregarding the error embedded in each kind of information. So if we want to have an idea of which is the accuracy of the forecast we are producing, we should not take into consideration only the error related to the statistical model that combines the deterministic ones. We should also take into consideration the error that is due to a set of operations that we have made in our GIS. Interpolation, aggregation, disaggregation, and so on. What's the impact of these errors on the final estimate? Well, I think that the question is clear. The answer is not so obvious, as you can imagine. Also because not only we have errors in each layer, we also have the propagation of the errors in the model. So how do the errors interact among them? The literature shows some approaches, and the first one is the most challenging, that is describing analytically the error that is associated to each information layer, and analytically describe the impact of the error on the different procedure following the error propagation. This is the most challenging, but indeed, it has never really been used. It's not difficult to understand why, because it's extremely complicated, and it's really valid only for a very specific problem. It cannot really be expanded to other situations. So you have to make a huge effort in order to try to create a model for the error propagation, and so on. And then you will have the results just for the specific case. Most of the literature is focusing on a posteriori analysis with specifically two aims: trying to understand which is the level of error included in the final model, and also for trying to simulate the problems which are related to the impact of the measure on the final model in order to minimize the impact of the errors. But this is done ex post. So first of all, you try to use all the different variables within the statistical model. You have the results, you try to understand what is going on, and go back in order to maybe have clearer ideas on the kind of GIS operations you have to do, you are allowed to do, you should do in order to minimize the error, the final error. Indeed, the most widely used approach is the simulation approach.
Elizabeth?
Thanks a lot. The simulation approach allows you to have an idea of which is the main impact on the final estimate of the different variables. So you can measure the impact of the different variables on the final estimate, and measure also the impact of the error embedded in the different variables on the final estimate. And also in this case, also in the case you use a simulation, you can try to have some ideas on which kind of measurements should be made in order to reduce the errors associated to the different operations that you do in the GIS. There are some other approaches which have been developed recently, indeed in completely different topics, but probably I will not have time to talk about this. I'll just show you this image in which we have the error associated to the aggregation of different areas when using small area estimators. So in case we have to aggregate data for adopting small area estimators, what's the impact on the error of the small area estimator? Here we have a set of different kinds of small area estimators, and we can see that after the aggregation, we have a very important increase of the error associated to C-bloop. This is very important because initially, without the aggregation, we had a very low level of error for this kind of small area estimator. So in principle, this should be preferred. But then we have to keep in mind that if we have to aggregate the data for integrating the different sets of variables, then we are going to have a higher error due to the fact that we are aggregating the data. And it's not surprising that we have the smallest increase for M quantile, since it's not parametric. Thank you very much for your kind attention.
Thank you, Elisabetta, for the excellent overview you have given about agricultural environment indicators, the DPSIR, and the analysis using various models. We will take questions at the last. Before I invite the next speaker, Salim Sheikh, to kind of come and make his presentation, there are two more presenters. I don't know whether they are here. I just want to make an announcement. Mr. Charles from Zimbabwe, are you here? No? Benjamin from Ghana? Benjamin Jabik from Ghana? So I think only we have two presentations, so you can take about half an hour, then we can have an interaction session where you can have questions for both the speakers. Salim Sheikh is from US and he will talk on role of climate distribution on world, US and Indian crop yields.
Thank you very much for the introduction, Chair. As I said, my name is, let me introduce myself. I'm from NDSU. It's in Fargo. It's close to Canada. I love that place. Originally, I'm from India. Left at the age of 23, and I lived in US for almost 25 years. So it's been a long time. So it's happy to come back home and have fun with the food. That's what I love the most. So with that, let me introduce myself again. My name is Salim. I'm a professor. I'm not a statistician, but an ag economist. But I teach two classes. One is analytical methods, and the second one is applied risk analysis. In analytical methods, I teach three main components. One is the statistical models. The second one is the linear programming models. And the last one is simulations. So you'll see the first two approaches in today's presentation. And then I also run a center, which is the Center for Farm Policy and Trade Studies, which is specifically deals with the farm policies, which have 12 titles in US, and then also deal with the historical trade agreements. That's part of my appointment at NDSU. So given that, let me outline the presentation. Let me start the introduction, and let me present the theoretical and empirical model. Let me describe the data set in a few slides, and I'll have the results, and then we can have some conclusions and discussions. So with the introduction, what I would like to do is I would like to take a different approach. I'm more a visual person, so let me try to see if I can make a case for the relationship between crop yields and climate change. So let me start with the world, okay? And let me show you the animations of crop yields, and then I'll take a look at the climate variables. So let me start with corn, and I'll show you 3 slides. And the reason why I'll show you is I'll tell in a minute when I go to the theoretical framework. So let's start with the crop yields. So these are the crop yields in hectograms, and it's by country for corn, and it's over time. So it changes over time. So just giving you a context. So you can see the top, the year is moving. So you can see the changes in the crop yields across countries over time. And the red ones are the lower yields, and the green ones are positive, or on the higher end. So this is truly the corn or the maize yields across different countries in the world that grow maize. So from this slide, we saw two things. One is there's changes over time, and the second one is there's changes across cross-sectional units. In our particular case, these are the countries. Now let's take a look at the second map, second animation, which looks at the difference between individual countries and the world yields. So this would tell us how different each individual country is relative to the whole world, okay? And once again, it's over time. The countries which are in green have higher crop yields compared to the other countries. Red is on the lower end. So this is the difference in the crop yields between individual country and the world yield. And then I'll show you the third graph or the animation. This is by country within its own region. It's not comparing across the whole world, but it's comparing each country within its own regions to see where it stands. Sorry, not that file. You don't see as much red in Africa as you did in the previous slide. But you see Canada red once, so that's because of environmental issues, not climate change. And you might want to focus on US, Africa, and India. Those are the three things that I should focus on in the presentation. I thought there was only 15 minutes, so I did not bring the Indian presentation. All I'm going to present is the world and the US. And I want you to pay close attention to the US part of it, because that's what I'm going to talk next. So this was the difference in terms of the crop yields by itself relative to the world, relative to the region. Then I have one more thing which is related to the income groups. And those are the three classification stratas, or the hierarchical modeling. The reason I showed that is why, because when you account for the changes, you need to account for that hierarchical changes before you get into the second stage. So given that, this is for corn, and I have those for the other three crops. If anybody's interested, let me know. If not, I'll switch over to the climate variables. So here is the one wherein we are looking at precipitation, and I'm looking here at the 4 movements. For the world, I'm just looking at 2 movements. The first movement is the average, the second movement is the standard deviation, the third movement is the skewness, and the fourth is the kurtosis. So those are the 4 movements that defines the distribution. So in this particular analysis, what I did is I looked at the 4 movements for the US. Why? Because the data set was available. And then for the world, wherein I looked at just the 2 movements for precipitation and temperature. So here, let me go ahead and present the precipitation with the first movement. So this is the first movement. As you can see, there's lower precipitation in sub-Saharan African countries. Let me show you the second movement. So the greener means there's less variation. And see, within Africa, it's green. What it's basically telling us is even though there's low precipitation, the variation in that precipitation is very, very less. That's why it's in the green color. So there's very less variation in terms of the amount of rainfall that the sub-Saharan countries receive. And so here, I'll draw your attention to the US. So it's uniform. So now let's take a look at, so what I did right now is I showed you the difference in terms of the crop yields over time across countries. Then I also showed you the precipitation or the climate variables or the changes in the climate variables with respect to the temperature and precipitation for the two movements. Now let me take a look at the US. So let me go with corn. And here is the one that I wanted to show you three graphs or three figures or three animations. Let's start with corn yield over time across counties. So this started in 1910. So the red color is the lower yield and the green color is the higher yield. And you can see when it shifted, when some of the countries from red became green. So that's an increase in crop yields. That's basically because of the technological innovations going over time. And you can see, I don't know if you saw yesterday's presentation from folks from NAS, they basically were showing the Midwestern area wherein you grow corn the most, and that's in that states. So what it tells us is it's not consistent. Even the crop yields are not consistent. They're changing over time. And space. Even though at the country level we saw that it was a big green blotch, here you can actually see that there's too much variation across counties within US. And I did not bring the Indian maps. When you look at the Indian maps, it's the same thing. It's quite different in terms of the districts. Boy, it's quite different between green states, the green revolution states versus the non-green revolution states in terms of the crop yield with respect to rice and wheat. Big difference. So the policies were skewed to one side. So this is the corn yield. Then let me show you the difference with respect to individual corn yield and the US crop yields. It's fun to watch. But it also has economics to it. Let me put it that way. And of course, there is statistics to it. I'll show you two more animations with respect to the climate variables. And then I wanted to focus on the four movements for the US. For the world, I showed just you two movements, the first and the second movement. And that has implications for the results that was estimated. So one more quick thing I want to point out. I know I'm saying this with tongue in a cheek, but to use US data set or to collect US's data set, it's like eating a pie or eating a cake. To collect data set for the whole world from FAO, it's like pulling a teeth. It's not easy to collect data set from FAO. Let me put that out there. And then let me show you the precipitation. So this is the first moment. and you see it's dry to the west, and that's why it's in lower, red color. So this is the average of the first movement, which is the averages. And by the way, the climate variables are based on the 30-year averages and the 30-year movements. That's typically based off of the climate literature. You just cannot use a yearly data set, but you need to look at the 30-year averages, variations, and the skewness and the kurtosis. So that's the average. Here is the second movement. It's quite similar, but it has different implications. What it's basically saying is the red color has the least variation in terms of the amount of precipitation that the counties to the west receive. And let me show you two more, and then we'll get into the actual presentation. So this is the third movement, and see how different it is. It's quite different. This is the skewness of precipitation. Instead of showing you the fourth movement, I just wanted to show you the temperature one. For me, it's fascinating and it's beautiful, actually, to be honest. See the patterns? It clearly shows where is the lower temperature, where is the intermediate temperatures, and where is the highest temperatures. So on the very north, it's pretty cold. And you can see those layers. It's so distinct bands. I thought that's fascinating when I look at it. Compared to the world or India, it's not like this consistent bands that we see in US. Okay, let me stop with this, and then let me go back to my presentation, and then I'll see if I can link that to what I was trying to show you. So what we tried to do, at least what I tried to do is with those graphs, is basically try to link the temporal changes across spatial units with respect to the crop yields. So you have a distinct variation within the crop yields, and then you have distinct variation between the climate variables. And the question becomes is how do we link those two to estimate the production use efficiency of those climate variables by commodities? So if you take a look at the historical literature, you can find literature with respect to economics and econometrics of yield and climate distribution. It's well established. They use simulation methods, they use statistical methods. Their primary emphasis is 3 C's. They always emphasize on the causes of the climate change. What is causing climate change? The second one is there causation between climate change? The third one was the cost of climate change. This is great. This is ex ante. My research in this particular framework is I'm not worried about what is causing climate change. All I'm worried about is what is the relationship between the existing conditions of climate change and the crop yields. So in this particular case, what I'm trying to do is trying to evaluate the crop-specific climate use efficiency. How efficiently is individual crops using the changes in the climate to maximize its output? That's what I was trying to see. Then I also looked at the shadow prices, but for this presentation, I'm going to stay away from shadow prices, and I'm just going to present the efficiency measures between the different commodities for these different climate variables. And then I'm basing this on the primal production function, wherein you use quantities of outputs and quantities of input. In our particular case, it's the yield, and then we have the climate variables. So in order to estimate the crop-specific efficiency use, I used a 2-stage approach. The first stage, I basically detrended the yields for time trends. As I just showed you in that animation, the trends are changing over time. They're not only changing over time, but also across cross-sectional units. And if you look at the difference between the individual counties and the national level in US or individual countries in the world, there's a big difference between the two. So what I'm suggesting in this particular case is we need to take those trends out, before we actually come back and say what is the impact of these climate variables on the trend. So if you look at most of the literature, what people do is they basically get the crop yields and then run that as a function of climate variables, which is great. But as we just saw in the graph or the animation, you need to account for the potential technology changes over time that is driving the crop yields. That's not our interest. Our interest is to evaluate what is the importance of the climate variables, not technology, the climate variables on the crop yields. So in this particular case, what I did is in the first stage is detrended the crop yields for potential time trends. And the second stage, what I did is I took the detrended yields and then run that as a function in a linear programming model to estimate the efficiency measures. So in order to do the detrending, I was trying to do that in the case of the DEA framework or the linear programming framework, but it's not that easy to statistically test. Why? Because it doesn't have any errors. So what I went back to is I went back to the linear and more specifically fixated on the nonlinear models to evaluate the potential trends after estimating it, testing it, and then took into account the nonlinear, the trends before coming up with the detrended values. So to do that one, in the second stage, what I did is I used the multidirectionals, and I'll show you why we used a multidirectional for the temperature and precipitation. So in this particular case, I used the 4 moments, which I just showed you. So that comes to the objectives. So the objective was to estimate the differential climate use efficiency by commodity and by the aggregation levels. So if you look at level, using world data set would be quite different than looking at the individual country at the county level for US or the district level for India would be quite different. So the data source that I used was US county data set for corn and soybean and wheat from 1949 to 2018. For the world, I used corn, soybean, rice, wheat from 1961 to 2016, and for Indian data set, I used corn, soybean, rice, and wheat from 1961 to 2016 as well. Now, coming to the theoretical framework. So the first one model was the statistical model, wherein you use a nonlinear statistical model to take out the trends. In the second one, we had to use a linear programming model, wherein I used a multidirectional DEA model. So in order to detrend the model, even though people like to use linear quadratic cubic trends, I think that's not appropriate given the empirical distribution of the crop yields. So what we looked at is we looked at the 5 models wherein it is representative of potential yield trend changes which is going on in US as well as in India and the world. So these are the 5 models. So these are subset within each other. So you can actually test which model is appropriate for the data set that you're using. And this was run by country over time, and this was run by counties over time as well. So this was the original straightforward time series model. Now we had to extend that to a hierarchical nonlinear model. Why? Because I just saw that analytical or the animation when we looked at the potential difference in terms of the crop yields by country and also by the difference in terms of individual country to the world, individual country to the region. So we need to account for the hierarchical structure of the crop yields wherein I represents the region, J represents the income group, and K represents the county. So we do need to account for the I, J, and K stratas that is available in the data set. That is for the world. For the US, what we did is we have the hierarchical structure wherein we have the nation, then we have the state, then the CRDs, and then the county. And then we have the time dimension. So we need to take into account the potential nonlinear trends in terms of modeling the trend estimations. Then once we detrended the model, then what we do is we come up with the detrended model, which we estimate using the max Y, which we just estimated, plus the absolute value of the error terms to come up with the detrended model. That's the state of art, straight out of statistics, nothing new, except this was done based on a hierarchical modeling. So once we estimate that detrended yields, then I use that as an input or an output model in the data envelopment analysis, which is a linear programming model. So in this particular case, what we did is we defined a technology wherein it had our outputs, which is the detrended trends, and then we had the input variables, which is the climate variables. So the climate variables were the 4 moments of temperature and the 4 moments of precipitation. And then we set this to an input requirement set wherein we estimated the input specific efficiency measures. So you can define this input set. This is straightforward from DEA modeling, nothing new, except that we extended that to the different directions. The different directions, what do I mean by different directions? Different directions of the efficiency measures. So the different directions basically could represent different directions of individual decision-making units, or the inputs, or in this particular case, for one particular input, multiple dimensions. And I won't go through the modeling, but this is what I would like to show. So if you're looking at it to the two variable scenario in the input requirement set, you can see that one particular specific point can be either horizontally towards the frontier or vertically towards the frontier, downwards, or in different directions. So the technically feasible ones are the max and the mins are the horizontal and vertical directions. And the inputs, or in this particular case, the decision-making units, or in this particular case, the inputs can move in any directions. So we wanted to make sure we account for the different possibilities. Why? Because we don't know a priori which particular county is moving towards the frontier or not, depending upon the climate variables. The same case with the countries, the same case with the districts in India. So what we did is we did a multi-directional approach wherein we estimated each of those arrows in terms of what's that theta value. Now with the data description, and I said before it was easy, it was like eating a pie to collect the data set from NAS. So you have county level data set from NAS, which is proofed, and it's pretty solid, pretty good data set. And then I restricted all the counties with minimum of 25 years. And then for the climate variables, what I did is I took the station level data set from NOAA, and then I estimated that to the county level. So basically developed a county level model. After constructing this monthly data set for the temperature and precipitation, what I did is, okay, sorry, I missed the other part. So for the world data set, what I did is I took the data set from FAO, and then I said FAO had just too many errors. Even to correlate the classification between FAO and the World Bank, boy, it was challenging. There were just too many errors, unlike NAS, which is cleaned up and easy to download and run the models. So I looked at 192 potential countries from 1961 to 2016. With Indian district data set, it took me, let me put it this way, it took me about 4 to 5 years to put this district level data set from 1961 to 2016. It was a challenging task, believe me. There were quite a few graduate students who spent some hours putting those data set together, but it was not fun. And I can still assure you, I don't know whether I have the right data set or not. But for the recent years, yeah, I have the good data set. But for the past years, reclassifying the newly defined states and the district was and is challenging. So that's not the reason I did not present. The reason I did not present is why? Because that paper is in review and then revise and resubmit. That's why I could not present it here. In any case, that's a deviation. So based on the monthly data set, what I did is I calculated the movements, the averages, variance, skewness, and kurtosis. So if you take a look at this particular two-way graph, you can actually calculate 8 potential four-movement distributions. But what I did for this particular paper is I just stuck with the mean of the average temperature, the variance of the average temperature, the skewness, and the kurtosis. Then you can also look at the other ones. I think that's purely based from stats. It has different connotations, different implications. Now here is the empirical application and the results. So with respect to the variables used at the US level, determined yields, then I went through the same average, variance, skewness, and kurtosis for temperature and precipitation. For the world country level data set, it was average temperature and then variance in temperature as well as precipitation. Now the US county results, I'll just show you the results instead of the numbers, and then with the other one, I'll show you the histograms. So here when we look at the efficient use of climate but these different crops, this is corn. So you can take a look, all the ones which are greener, they're using their climate efficiently to maximize their output. So it's not consistent even within US that each individual county is using climate variables efficiently. So this is on the top left, it's the average, on the top right, it's the variance, and the bottom left, it's the number of days, and the right side, it's the maximum precipitation. Now you take a look at soybean. It's once again a little bit different, and once again you can see different variations across the 4 movements. Then you look at the wheat. which is totally different and widely grown in US, you can see a difference in terms of the efficiency measures. What it basically tells me is that there's a difference in terms of the efficient use of the climate variables by the individual commodities and the cross-sectional units. Now, the reason we wanted to look at multiple directions is why? Because when you look at the different directions, you can see that the climate variable, this is the average precipitation, the different directions gives us the different efficiency measures. The horizontal axis gives us the efficiency measures. So it's quite different even with the different directions. So what I did is we basically looked at the total directions, then have an average of those. The reason I'm showing you is that the distribution is quite different when you look at the average, when you look at the variance, when you look at the skewness, and when you look at the kurtosis. Quite different. And when conclusions, does directions matter in terms of estimating the efficient use? Yes, it does matter with respect to the climate use efficiency. Precipitation temperature had monotonic effect of the 4 moments. That means the average had the lowest effect, followed kurtosis has the highest effect, followed by skewness, followed by variance, followed by kurtosis, followed by averages. So it's in that higher moments. It's monotonic. However, when you look at the skewness and kurtosis, they had a higher effect in terms of its contribution to the changes in the crop yields. Now, with respect to the world country results, so I basically looked at the different distributions or the histogram with respect to corn, rice, soybean, and wheat. As you can see, there's a difference in terms of the efficient use of this temperature by these different crops. So wanted to see if there's any difference between the crops in the use of these climate variables. So in terms of the temperature, sure enough, you can see rice and soybeans which are using it efficiently. Why? Because the histogram is skewed more towards the right side. Not skewed, but it's more towards the right side. The mean is more toward the right side compared to the maize and wheat. Then we take a look at the second moment. It shows similar results with the mean towards the right for rice and soybean. And then with the precipitation, the same thing with respect to the first moment, second moment. And then what I did is I said, let's see if we can disaggregate these effects by region. So if you take a look at the regions, we have 7 regions. And then it's so clear and so distinct that you look at these different regions, and sure enough, North America stands out in being efficient. And it being closer, the mean is closer. There's not much variation compared to these other regions. Quite a bit of variation compared to North America, whereas US part of it. So that's with respect to the first moment. With respect to the precipitation, once again, the same thing. You can see North America very high efficiency with lower variation in terms of its efficiency. So to conclude, as we expected, the crop-specific climate use efficiency is different for temperature versus precipitation, and is different for regions and countries of the world. With that, thank you for listening. If you have any questions, I think we are scheduled to have it at the end, but I like to have the quote at the very end. I enjoy what I do. If I don't, it's not easy to work your way through in terms of whatever you try to do. So given that, let me stop.
Thank you, Salim, for such a exhaustive, animation, analysis, and, exciting, results and conclusion. Now, since we do not have the other 2 speakers, we have about 20 minutes of left for the session. So I have my own questions, but I'll reserve it for the last. So from the speakers, of course. So what we have had is both of them had talked about the importance of measuring climate change, analyzing the impact, and which will provide the policy makers the road to achieving the sustainable development goals through change in agriculture. The change in agriculture, in fact, in India, if you, he has failed to, I think, mention, is that the contribution of agriculture to the greenhouse gas emission is roughly the same size as the GVA. It's about 16 to 17%. Okay, so now there is one aspect of it is that we can look at it from purely from climate change perspective. The other thing is from environmental perspective. Much of the crops which are grown in some parts of the country have lot of resource intensity, particularly water, and it has its implications for the environment because groundwater is getting depleted very fast. So these two presentations covered a certain aspect of it. There are certain more aspects. Perhaps if we had had the other two presentations, we would have had a better view. But they were not able to come. Now I would request the audience to please raise questions to the speakers. Please be brief in your questions. Introduce yourself first. Ask whom the question is directed, and then we'll take it forward from there. If you want to give your own version, we can reserve it for the later. Some people have a comment more than a question, so comments will save it for the last. Questions, please. Floor is yours. The gentleman there.
In the United States across time, thinking about North Dakota, where you're out of, obviously the soybean area has changed quite dramatically, for example. So I'm curious if that gave you any challenges in terms of your analysis as soybeans became more predominant growing there. And conversely, in the past few years in the United States, the amount of wheat acreage has declined relatively dramatically. What impact did that have on your analysis? And then maybe you could talk just a little bit, I'm trying to get in my mind, when we think of the Great Plains, high variability in temperature and also rainfall and the periodicity of the rainfall as compared to that, what we think of the Eastern Corn Belt where things tend to be more stable. How do I think about the results that you offer? Thanks.
Thanks, Joe. Good question. I know you come from you. So let me show you the slide that I was supposed to and I did not. Let me show you a map, and I think that is what I think you're alluding to. So here is the soybeans, not the world. I was looking at the US. So let's take a look at the 4 moments, Joe. So let's start with the average precipitation. So it's pretty bland in the I states for soybeans in terms of the averages. And here is the efficiency measures. This basically tells us how efficiently is soybean using the average precipitation, and here are the ranges. So the lighter green color is less than 50% efficient. So what it basically tells us certain counties, they're not as effective as what it should be. For example, we always pride in North Dakota saying that our soybean is the best variety of, and then it's organic that we export the most. And so we pride on it, but what we are beginning to realize is it's not as efficient as we think in terms of using its own thing. Now, with respect to the changes in the acres, Joe, let me finish this one up and then let me visit with respect to the acres as well. So this was with respect to the average. This was with respect to the, sorry, I wanted to show you the temperature as well. The average temperature, not much. Over time, that is consistent over time. Then if you look at the variance, it's the same thing. But if you take a look at the skewness, it's way different. So the first two movements really did not matter even which county it is in terms of the soybeans. What mattered was the skewness and the kurtosis. That was the one. Because if you look at that and compare that to crop insurance, most of the payments that are made are because it's left skewed or right skewed. That's why they get paid. And that's what we observed in terms of the precipitation data set. So that's in relation to what question you were asking. Hopefully I answered that question. The second part is when we looked at, there was a different paper that I'm looking at, wherein we looked at what is contributing to the changes in the acreages between corn, soybean, and wheat. And what we found is it was not the prices per se that was driving it, but it was the climate variables that was actually driving that changes in the acreages. First off, the farm policy. Those are the two variables rather than the price, where in economics we always think, oh, it's the price that drives it. But it was actually the climate variables and the farm policy that was driving the changes. That's what we found out with respect to the difference in terms of the efficiency measures in soybean between the Midwestern and the Northern Great Plain states. So there was difference in terms of the efficiency measures. You're absolutely right on that one. But it did change over time. We became a little bit more efficient. We are catching up to the frontier.
Any other person would like to ask any question? I don't see any question. So I will misuse the privilege of being the chair and then ask from both of them a question. See, what we are looking for from the researchers, statistician analysis, from the policy perspective is that if you have to move towards these sustainable development goals, whether in terms of climate use efficiency or resource intensive use, less resource intensive agriculture, what would be the kind of data set which will help us set the policies, and whether policies can be set without affecting the incentive paradigm, because ultimately the farmer is not going to shift unless the economics works out that way. So I would like to ask from you, this is a slightly analytical question, maybe not in the same thing what you have said. If we have to identify that we need to shift the land use and land use change to a more sustainable system, what would be the kind of indicators and what would be the kind of incentives that would be required?
Thanks for the question. It's nothing what I did, but I did answer that question in my dissertation about 20 years ago in Nebraska. So in that particular instant, what I did was I estimated the environmentally adjusted productivity measures for Nebraska. One thing I knew about Nebraska or in general US was the Clean Air Act in 1972. So at least in Nebraska, what I found is from 1972 to 1980, the farmers were complaining about, do we need to have a restriction in terms of the amount of fertilizer we use? But what they did is they adapted themselves, and by 1980 or 1985, the nitrogen use was peaked. So the pollution from nitrogen reduced. So what I call that in my dissertation was a Porter hypothesis. So it is more how do we accurately measure it rather than having a policy or an incentive. So what I found in that dissertation is if you don't account for the environment, post-1980, we underestimated the productivity measures. When we accounted for the environmental pollution, we actually are supposed to be on a higher productivity trend. So my take on that one is it's more how the producers adapt to the new changes in a positive way without having any externalities. At least that's my quick take on that one. Thank you.
Is there time for one more question?
We'll wait for thanking. You can do.
Any other question in the meanwhile? If anybody has,
I have one more question, if I may. Again, Joe Parsons, USDA. For both the presenters, you wound up using, for ground truth, Elisabetta, and Salim used a lot of data from around the world, and I'm going to give a shameless pitch for a talk that I'm doing after lunch. But we're thinking about how we go about disseminating information from our agency, because we know there's a very wide variety of users out there, and I think this is a challenge for really everybody at a national statistical organization, is how do you best disseminate data to meet a wide variety of users, and as data users, do you have any advice for us to think about how to best do that in 2019?
Yeah, I used some ground truth data collected by the Italian Ministry of Agriculture and also the declaration of the farmers. And it was not so easy to have this data. I had the chance to use those data just because I have been involved in the programs of the Ministry of Agriculture since a long time ago. Otherwise, I couldn't, because they had to rely on the fact that for sure, I'll not disclose the data. So there are some privacy problems associated to the data. That is the privacy of the farms. So if the farmers care about their privacy, and this is the case, it's not easy to make the data available. And sorry, may I ask a question? Still, to him.
Okay.
Not to the audience, but maybe also to the audience. Now, still concerning the data, of course, you have no problems about the data from NASA and from USDA, from NAS, but you also said you had many troubles in using the data of FAO. But my question is about the level of aggregation of the data, because in the US you use the county level, but all over the world, for sure, you didn't have the possibility to have data with this kind of granularity. What kind of data did you use, indeed?
Yeah, for the World Bank. Joe, let me answer your question. I think that's a good thing that we're struggling with in North Dakota, to be very honest with you. So one of the things that I'm working at North Dakota was with the commodity groups. So we're working, at least I'm working with the farm policy issue and the trade issues with respect to soybeans and corn, and then sugar kicked in recently, and then the dry beans also kicked in recently. One of the things that we focused quite a bit is how is it possible for us as a user to link the NAS data set to RMA data set to FSA data set. So I know there was one program that was going around, Midas or something like that. Yeah, so that was going around. We were hoping for that one to come through, and then what we were struggling with is how do we very easily integrate those variables, if not at the individual producer level, at least at some kind of an aggregate county level or even plot level data set that would be great for our analysis purposes, because we were looking at alternative crop insurance policies for corn and soybean with respect to prevent plant, and we had zero data set for that one to integrate between the three. That is one thing. But I still like the way NAS gives us the data set. I know I've been in conversation with NAS for the past 10 years, and right now it's very nicely set up wherein you can download this Z file or G file, and then I run through a SAS code, so it'll clean up for a day it'll take, but it'll clean up the whole thing, it'll give me what I want. But I was trying to do the same thing for the FAO data set. So what I found inconsistency with the FAO data set is the country names were quite different in FAO versus the World Bank versus the UN. But all three are under the same common authority or something like that. So what was strange is you have so many ways of presenting it. Even the three-way code, they're different. Even the numerical three-way code, they're different with changes between the three groups. So it was very challenging. The only reason I was able to work through this was because I have a couple of students who actually worked on their master's theses. One was working on the sub-Saharan countries. He took a long time to get that fixed. But with respect to the FAO data set, even the quality of the FAO data set is always, how do I want to put it? I'm second guessing myself. Why? Because what I did is I compared for this study, I compared the corn yields from NAS, and then I tried to transfer the hectograms into bushels. and it did not converge very well. But I ended up believing NAS because I know what NAS is. But for me, it's hard to believe FAO. The other thing, I don't want to throw FAO under the bus, but even if you send an email to FAO, they're notorious not to return calls. So in any case, I don't want to throw FAO under the bus, but that's the way it is. Even for clarification purposes, you don't receive an email. So I was thinking, boy, they must be just too busy. So I just let that thing go, and I used the official data set. One more case of point I want to make with respect to one more student from Turkey who's actually looking at the productivity measures using FAO data set. What he found is the units of the prices, because he is from Turkey, he knows it. So there was a shift, or there was an inflation. So the price values was in 2 digits, and then the very next year it was in 6 digits. And it took me a long time to figure it out before I called him and asked him, so what's going on here? Oh, he said, yeah, sure, it's inflation. How would I know? I'm not from Turkey. How would I know? So if there was some explanation by the FAO to say, okay, here are the issues that needs to be taken care of when you use the data set, something like a disclaimer. I know there's a default disclaimer, but a disclaimer with respect to specific variables that needs to be used. So I don't know, I try to pitch in my 2 cents worth of comments to them, but it goes deaf ears, let me put it that way. But NAS, it's great to work with NAS, I have to put it that way, Joe. Thank you.
No, my question was not on the quality of FAO data, since I'm not representing FAO here. It was about the level of aggregation of the data and the impact on your analysis.
So with respect to the level of the aggregation, the only data set they had was at the country level, wherein that's the only way that you can have it.
And what's the impact on your analysis? That's my question.
So what impact did it have? If I compared the state, the country level data set from FAO and compared the same US implications versus the using of actual US data set, 2 different numbers. So for me, I'll be biased again. I think I'll stick with the numbers from USDA. That's my take.
Thank you, Salim. I think we have almost come to the end of this session. We have had 2 excellent presentations, and of course a lively question and answer session also. So the takeaway is that there are a lot of tools and analysis which are available, which was presented by both the speakers to understand the impact of climate change and the kind of the agro-environmental indicators which they threw up. So, but lot more needs to be done, particularly because at a aggregate country level, as he said, country level or a global level, parameters will be slightly different because yield varies according to climatic condition, agroclimatic region. So we may have a longitudinal or latitudinal kind of a benchmark before we can compare, or we can contrast the outcome in terms of resource use efficiency or climate use efficiency. So with these words, let me thank the panelists as well as the audience for their excellent participation. I would ask the organizer to propose the formal vote of thanks.
So, good morning, everybody. So, from the organizer side, it is my duty to make the vote of thanks. I thank the chair, Dr. K.L. Prasad, for successfully conducting this very small but very lively session. And I thank both the speakers, Dr. Elizabeth and Dr. Salim. He was very responsive for whatever the question, and he made this session very lively. And I thank all the delegates for being here, for raising their questions. I think that makes the purpose of this conference, and I hope you must have all enjoyed your stay in Delhi. And thank you all for this. Thank you very much.